Hi everyone and welcome to my YouTube channel. In this video, we'll be wrapping up the algebraic manipulations that we've been discussing so far in the inequalities playlist. So far, we've discussed many techniques like the Ravi transformations in order to handle the side lengths condition of a triangle. We also discussed then the homogenization technique. It was a very powerful technique in order to get rid of the ugly conditions. We also discussed the substitution technique, and we saw that many cases, many inequalities, the condition can be easily handled by simply doing some magical substitution, like the trig substitutions and the other substitutions that we discussed, like the ABC equals 1. So in today's video, we'll be wrapping up these algebraic manipulations with a topic, or with a technique actually, that's sometimes called dehomogenization, and sometimes it's called the normalization. So what are you waiting for? Let's get started. Alright, so first of all, let's explain what exactly is this technique, normalization. What does it mean? So far, if you remember, we've discussed the technique homogenization. The homogenization technique, we said that whenever we have a homogeneous inequality, what does that mean? That means, let's say we have three variables a, b, and c. Now we want to prove some inequality. Let's call like the inequality argument, whether it's correct or not. Let's call it p a, b, c. You want to prove that this is true, that the inequality is indeed correct. We said that if the inequality is homogeneous, then that means when we substitute ka, kb, kc, where k is positive number, then it's actually equivalent, like the k will get cancelled, right? So you kind of just, if you want to prove this, then it's equivalent to proving this, to proving the same inequality, but with new variables that are ka, kb, kc, because the k will get cancelled from both sides. We saw many examples so far. In fact, most of our inequalities were homogeneous. So basically, when we have a homogeneous inequality, you can actually, instead of working with the original ABC, you can work with modified ABC. But how can we modify them? We can just modify them like this, by introducing a new k, right? K, such that we have now new variables ka, kb, kc. Actually, this k is powerful because you can actually define it whatever you want. So for example, let's see if we pick k to be 1 over cubic root of ABC. Now, if we call the new variables x, y, z, so now we basically want to prove p x, y, z, the inequality for x, y, z. Now, if you look at these new numbers, if you take their product, what is the product x, y, z? It's actually pi a over cubic root ABC. Of course, this thing is ABC over the cubic root of ABC cube, and that's actually 1. So guess what? Now, instead of proving the same like the original inequality, the homogeneous inequality, now we'll be working with a new inequality, but with a condition such that the product of the numbers is 1. Now, of course, the new inequality is not homogeneous, but at least we have a condition. So yeah, in fact, this thing is called the dehomogenization, because here we're doing the opposite. In the homogenization technique, we had some inequality. We want to get rid of the condition, so we just try to homogenize it, and now we're done with the condition. We don't want to think about it. Here, actually, we're doing the opposite. You might be wondering why exactly we're doing this. We want our inequalities to be homogenized, right? Well, actually, not always. It depends on the question. Sometimes you might have 3 variables, let's say, but when you dehomogenize, you actually have 2 variables. So working with 2 variables is easier than working with 3. So it really depends on the specific question that you're doing. Sometimes if it was homogeneous, it will be easier. Sometimes the opposite. How do you know exactly? Well, you should try. If your inequality is homogeneous, try thinking about dehomogenizing it or normalizing it. Do you think it will be better, easier? If you think so, then yeah, go ahead. And of course, as you can see, you can actually choose this k to be many stuff. here we just choose this thing in order to give us product is 1. In fact, you can also assume the sum is 1. How exactly can you make the sum 1? Think about it. What should you choose as k? If you want the sum to be 1, then always just think about it like this. You want sigma ka to be 1. So what does that mean? K is equal to 1 over sigma a. So by this choice of k, you can assume that their sum is 1. And so on. You can actually do whatever you want. You can actually assume sigma AB is 1, sigma AB is 3, whatever you want. For each one of them, you can choose some k. Okay, so keep that in mind. Always, in order to check whether you can do something, just try to solve the equation and see what is the k. Anyway, right now let's move to practical examples. In this video, we'll be solving 2 practical examples, and we'll be seeing that this technique, whether it's powerful or not really. So let's go. Alright, so our first example here is from the JBMO, which is the Junior Balkan Math Olympiad shortlist 2019. As you can see, it is an A6 question. So we're given here ABC, positive numbers, and we need to prove the following inequality. If you take a look at this inequality, we have 3 variables, A, B, and C. Okay, if you try to look at this inequality, you can easily see that it's not symmetric. Clearly, it's not symmetric at all. But is it homogeneous? Well, the degree here is 2. Here is -1. So this thing is degree 1. This thing degree 2. This thing is -1. So yeah, degree 1 again. This thing is degree 1. So yes, it is homogeneous, which is good. Okay, what exactly do you want to do here? If you also observe more, look at this, you will notice something. Look here. This thing is homogeneous, is symmetric actually. If you just look at A and C, in terms of A and C, this thing is indeed symmetric. If you look here, if you just focus on A and C, this thing is symmetric with A and C, and this thing is just A plus C. So yeah, it's symmetric for A and C. If you look at this, again, just for A and C, this thing has C, this thing has A, so yeah, it's symmetric for A and C. And finally, this thing is symmetric with respect to A and C. So if you just consider A and C, then all of this is symmetric. The only problem is B. B is ruining everything here. So basically our plan here is simple. We want to get rid of this ugly B that's ruining everything for us. How can we get rid of it? Well, remember, this thing is homogeneous. So we can normalize. We can replace ABC with KA, KB, KC. So how can we choose K in order to get rid of the B? Very easy. Just choose K to be 1 over B. Now you'll have A over B 1 and C over B, and make this a new variable X and this thing Y. This thing is 1. So now I can actually do the same inequality, making actually with A and C again, but B I will just assume that B is 1. By the way, you don't really necessarily need to do all of that. You can just say because the inequality is homogeneous, we can assume B is 1. So here we can just say assume B is 1. Of course, you can say that you can do this because it's homogeneous here. So write the explanation here. Okay, now if you assume B is 1, we can rewrite the inequality by getting rid of the B. So let's do that. So now we just want to show that this thing plus 1 over A plus C plus, okay, we got rid of the B square. Now it's just A plus A. Okay, I just changed the order. A plus 1 with C plus 1 here. Just swap the order here. And greater than A plus C plus 1. Okay, so this is what we want to prove. As you can see, this is way nicer because we just have now 2 variables and everything is symmetric with respect to A and C. In fact, here there is a very nice trick you can do. Whenever you have symmetric stuff, like right now we have 2 variables and everything is symmetric. In fact, if you expand everything, you will get a symmetric polynomial, right? So when you have this, sometimes it's useful to replace your variables, right? Instead of dealing with A and C, you can deal with the sum and the product. What does that mean? So assume that S is A plus C, the sum, and P the product, AC. Then you should know that any symmetric polynomial that has two variables A and C can be always written using S and P. For example, let's say you have this A squared plus C squared plus AB maybe, or plus AC. That's basically the same as this thing. How can we write it using S and P? Very easy. Look here. How can this thing, of course, you know it's A plus C all squared minus 2AC. So you can just write it as S squared minus 2P. And then this thing is plus P, so it became S squared minus P. So as you can see, this thing is really nice because you can, instead of dealing with it like A and C, you can now escape to work with S and P. Sometimes this thing is nicer. Working with S and P is nicer than working with A and C. Actually here, clearly it's nicer because look here, this thing is S. This thing here is S. This thing here you can play with it, and this thing here is already S plus 1. So yeah, probably we should be working with S and P. That will be nicer. Of course, is this only special for the working with two variables? What about three variables? Actually, you have the same thing, but there you should be working with three stuff. Sigma A, let's call Q, sigma AB, and the product ABC. You can write any symmetric polynomial that has three variables using these three numbers S, Q, and P. The sum, the pairwise sum, and the product. Okay, so keep that in mind. This is really a useful technique. That's helpful sometimes. Okay, so right now we'll be doing this because, as we said, everything nearly is kind of S. So let's just do that. So let me erase everything here and express everything using S and P. So let S be like A plus C and P be AC. Now our inequality is the same as we said, this thing here is just S squared minus P. This thing here is 1 over S plus 1 over S plus, okay, now this thing is in total symmetric, so we need to work with it. So it's going to be A plus C plus A plus 1. So it's basically S plus 2 divided by A plus 1 times C plus 1. That is basically AC, which is P, plus S plus 1. So yeah, just like that, greater than S plus 1. Okay, very nice. Now this thing is much nicer, and now the plan is very simple. We're going to expand everything and get a really nice polynomial. You can see that it's not going to have very large degree. So I'm going to leave you to just expand this. Of course, you just be multiplying by S times S plus 1 times P plus S plus 1, which is really doable and easy. So I'll immediately be writing the expansion and the after simplification. So you can compare what you got with my work. So we'll be getting S to the 4 plus S cubed plus S squared plus S cubed P. Of course, you should not be saying, oh, this is we need to expand all of that, because so far right now, if you've been following the playlist, we've done way uglier expansions than this. Remember the IMO problem 3? Yeah, that sure broke our hands. So this thing is considered a piece of cake for this, compared with that one. Okay, so this one here, 4PS plus P squared plus P. Okay, so this is exactly what we want to prove. So now, if you look at this new inequality that we want to work with, is a polynomial, and we need to compare these guys. But here we have a problem. How can we exactly compare between S and P? Well, there is something here that you should know. When we're working with A and C, we don't have any inequality that links A and C, because A is anything and C is anything, right? But when we're working with S and P, we're working with the sum and the product, and we do have an inequality between them. You know, the simplest inequality actually is the AMGM. So we know, for example, that S squared is greater than or equal to, like A plus C all squared is greater than 4AC. So it's greater than 4P. So you should keep that in mind. This inequality, you should keep it in mind. In fact, we'll be taking this and using it to guide us what exactly should we like try to apply. Let's keep that one here and see how we can manage this one. Of course, as you can see, you should be trying to get rid of the s. The s are the bad stuff because they are the big things, right? S is bigger than kind of p. This not really s is greater than p, but I mean this should be your mentality, what you should be working on. You want to get rid of these s here. So for example, which one is worse, this or this? No, this one is worse, right? Because it has s squared. Okay, so let's try. Like fortunately we have tons of s here, so these are going to be very good for us. So let's try to get rid of these guys here. First of all, with the worst one, because it has s squared. Okay, in order to get rid of this one, we're going to be using the like the best one for us on the LHS, greatest one. This one, right? S to the 4. So we know that s to the 4 is equal to s squared times s squared. That's greater than 4p s squared. Nice. So that means this thing kills this, cancels this, and now we just have a single ps squared, right, on the RHS. So now this thing ends this, and we have an additional ps squared here. I'm going to be leaving these like here, what we'll be like having. Okay, so we're done with both of these, and we have now ps squared. Let's move on. We have this and we have this. Which one is worse? Of course this, because it has an s and a p squared. This one has only p and s. So let's try to get rid of this. So in order to get rid of this, which one should we pick? Probably this, right? Because this one is s squared, we can replace it with p. So you can just say s cubed equals s times s squared, which is greater than 4ps. Wait, this one actually is not suitable. This one in fact killed this, right? Okay, that's good actually. So we're done with this one and this one. But no, we want to get rid of this. How can we get rid of this? Well, for sure we have a better one than s cubed. We have an s cubed p, right? S cubed p. So let's try to kill this with this. S cubed p is equal to s squared times sp, which is greater than 4p times that thing, so 4p squared s. Okay, now this thing is nice, because as you can see, here we got 4, here we have 2, so in fact we can here just add 2p squared s. Okay, good. So now we just have this weak stuff. We can kill them like very easily, get rid of them. So we have p squared. How can we get rid of the p squared? Okay, very easy. Let's for example pick what exactly. So first of all, actually the s squared here, we can apply 4p to get rid of the p here. So this can get rid of this, and we'll be having here plus 3p. Now we have a p squared. How can we get rid of the p squared? Think about it. How can you get rid of the p squared? Well, you cannot really use the s here. Remember, you don't really have to be working with these guys here. You can be working with these, because these are the remaining ones, right? So do you think any one of these is suitable to get rid of the p squared? Well, clearly you can work with this, right? Because you know that ps squared is greater than 4p squared. So yeah, that actually finished it. So now we're having here just instead of this thing here, we can replace it with a 3p squared, right? Okay, now of course here we have 0, and we still have an s. And so the inequality, basically, if we apply these inequalities, then we just need to prove this. And clearly this thing is correct, because these guys are positive. And that means we're done. In fact, there is no equality, as you can see actually here from the original question. We have strictly greater than. So yeah, that finished it. So as you can see, the only thing we did here, we assumed b is 1, we normalized, and then we just use this idea, everything is symmetric, so work with these instead, and then we just expanded and applied simple AMGM. Okay, so now let's move on to our next example. Alright, so our second example is from the USA Junior Math Olympiad 2018, problem 2. This one is pretty famous question because it's kind of a strange question. Let's see why. So we're having A, B, C positive numbers, and we have this condition, sigma A equals 4 cubic root of ABC. So this is our condition here. Not really nice condition. We're asked to prove that this inequality hold to sigma AB plus 4 the minimum of like A squared, B squared, C squared greater than sum of A squared. So here actually we have two weird stuff. We have the minimum function here, and we have this condition. So of course, first of all, how do we handle something like this, a minimum? How can we be working with this? Very easy. As you can see, everything is symmetric. So you can just assume that A is bigger than B, bigger than C, right? You can order them. So we immediately can say assume, without loss of generality, that you don't really care, you just want to have the minimum. But anyway, you can do this. So now our inequality is the same as doing like this. 2 sigma AB plus 4 C square is greater than or equal to sigma A square. In fact, you can just cancel here and get this thing. 2 sigma AB plus 3C square greater than A square plus B square. So this is basically our inequality, right? This is what we want to prove. And this is our condition, don't forget. Now actually, if you take a look at our inequality, you can see that degree 2, it's homogeneous. So that means we can use normalization here, and you can assume stuff like sigma AB or ABC equals something, right? Be careful, this is actually incorrect, because we have a condition here. So it's true, you can replace this thing with KA, KB, KC, but don't forget that you have a condition here. So now K will actually appear here. But actually, if you take a look here, this thing is degree 1, this thing is also degree 1, because cubic root of like ABC is degree 1. So that means that if you put the KA, KB, KC here, then also they will cancel from here and here, because both of them are homogeneous. So this is really a weird situation, since the condition itself is homogeneous, which means that you can actually assume whatever you want. You can normalize here both the condition and the inequality, no problem at all. So that means you can do whatever you want. So what do you suggest? How can you like normalize in order to make the condition really look nice? Well, in my opinion, the best thing to do is setting getting rid of the cubic root by setting ABC 1. If you set ABC equals 1, then automatically you get from the condition sigma A is 4. So now you can assume ABC equals 1, and that just gives you sigma A is 4. And now, as you can see, you have this, you have this. So actually you have tons of stuff. So in order to use that, basically what we'll be doing is looking at our original inequality that we'll be working with, and trying to use what we already know. So if you take a look here, what do we have? We have a sigma AB, and here we have A square plus B square, and here we have a C square. So how can we use what we know, the ABC equals 1 and sigma A equals 4 in these kinds of situations here? Well, clearly you want to have something related to sigma A, AB, and something that has A square and B square, so kind of sigma A square, right? And of course, we already know this thing is very helpful for that, because we know already that if we square this thing, we're going to get sigma A square plus 2 sigma AB is equal to 16. So that means this 2 sigma AB here, 2 sigma AB, we can write it using the sigma A square, and then perhaps we're going to get some nice stuff. So let's do that. We're going to substitute 2 sigma AB with 16 minus sigma A square. Let's go ahead and substitute that. So what we want to prove is the same as 16 minus sigma A square plus 3C square is greater than or equal to A square plus B square. Okay, let's fix this. Okay, 16 is still here. Minus A square minus B square minus C square. This thing became plus 2C square. And now we move this to the right hand side. We have 2 A square plus B square. Okay, we can divide by 2, of course. 8 plus C square is greater than a square plus b square. Very nice. So now we just need to prove this thing. Okay, how can you prove this? Remember, we know that sigma a is 4, we know abc is 1. How can we use this to prove what we want? So now actually, you can see that we have kind of two equations here, right? Two relations. So that means we can kind of substitute. We can actually this a square plus b square, try to write it in terms of c. And that will just give us one inequality, a single inequality with a single variable. Can we do that? Let's see. Well, we know a square plus b square. We can write it using a plus b, right? So this thing, in fact, is just equal to a plus b square minus 2ab. Very good. Guess what? What's a plus b? We already know that a plus b plus c is 4. So this thing is just 4 minus c squared. And guess what? ab, we already know abc is 1. So that means ab is 1 over c. So minus 2 over c. Very nice. So now what we want to prove is a plus c square is greater than or equal to, let's expand that, 16 plus c square minus 8c minus 2 over c. This is what we want to prove. Let's fix this. So here 8 with 16 is going to become 8, and the c square with c square is going to cancel. And now basically what we want to prove is 8 here, 8c plus 2 over c. We can actually divide by 2. 4, 1, 4. Is this true? What do you think? Of course it is. This is AMGM, right? This is correct by AMGM. So basically that means we're done. Because of course this thing is greater than 2 times the product of this under the square root, and this under the square root is just 2, so 2 times 2 is 4. And hence actually the equality holds when these two guys are equal. So that's equivalent to saying c square is equal to 1 over 4, or saying that c is equal 1 over 2, right? C is equal to 1 over 2. And then you can just equate all the equalities that we did. For example, here we have c is 1 over 2. Now we can solve the equations actually. This one here and this one here, right? Okay, I will leave this to you. It's very easy task to get the values for a and b. But anyway, we're done with this. So as you can see, what we did here is very simple. We saw that everything is homogenized, both the conditions and the condition and the original inequality. So we just normalized to make everything nice, and then everything was kind of a piece of cake. We just turned it into a single inequality with a single variable. And this is like a very powerful example on normalization. As you see, not always we want to homogenize. Sometimes we want to actually normalize. Why? Because we want to reduce the number of variables. If we just have a single variable, it's going to become way easier for us. We can actually sometimes use calculus like ideas or tricks when you just have a single inequality with a single variable. So you should actually balance between homogenization and normalization. You see the question and you really choose what you want to do. Alright, as a summary, today we learned the new technique of normalization, which is, as we said, also called dehomogenization, because it's actually the opposite of homogenizing, right? Sometimes we want to homogenize to get rid of the condition. Sometimes we want to do the opposite. We have a homogeneous inequality, but for some reason we want to dehomogenize it in order to get some nice condition that's going to make our life easier. Sometimes maybe to reduce the number of variables, like the example 2. Sometimes because we have a nasty variable we want to get rid of that's making our life difficult, like example 1. So let's quickly see what were these examples. The example 1, we saw that everything is symmetric. It's of course homogeneous. Everything is symmetric except the b. The b is ruining everything. So why not getting rid of the b? Can we do that? Sure. We can just assume b is 1 here. We assume b is 1, and then we just use the idea that everything is symmetric, and we see a bunch of a plus c, a plus c, a plus c everywhere. So we can use this idea of representing everything using s, the sum, and the p, the product. We just did that, expanded, and we never forget that s square is greater than or equal to 4p. By the way, you can, in some harder questions where you have 3 variables, a, b, and c, and you don't really get rid of them, you should also remember that if you can write it using s P and Q, which is the pairwise sum, the pairwise sum basically, A plus B, AB plus BC plus CA, sigma AB. And you should also remember that you also have relations between these guys. These are not super random. Just like you have inequality here, you also have inequality between S like Q and P when you have three variables. So sometimes you need to exploit all of these. In fact, you have tons of relations between these guys in terms of inequalities. You can relate S to P with AMGM, Q with P with AMGM, SQ with P also with AMGM, and you have actually other ways to do it as well. Some more complicated. Yeah, you should depending on the question, you should use the right one. Anyway, right now we just have two variables, and our life was very easy. We easily killed that question. For example 2, here this example was a little strange because we were given a condition, and still the condition was homogeneous, just like the original inequality. So that means we can actually normalize here, and when we normalize, we just make our life easier because this thing becomes 1 and this thing becomes 4. So now we can just quickly deal with this and turn it into a single variable inequality and easily crack this JMO question. Alright, so right now finally we're done with the algebraic manipulations, and in the next lesson we'll be starting with a new inequality that's really important, that's called the rearrangement inequality. So I hope you guys enjoyed this video. Please like, share and subscribe to the channel, and don't forget to join the Discord server as well, and see you guys in the next video.